Okay, so my name is Anand Talwad. Hello, everyone. I am a technical marketing engineer with CX Switching TME team. And today I am going to talk about AOS-CX 10.15 update on in-band flow analyzer, a new feature we are bringing in our AOS-CX switches. So let's get started. Okay, so the agenda is pretty much generic. We will start with overview, look at some use cases, dive deep into details, configurations, best practices, troubleshooting, and finally, and with a demo. So moving towards the overview section, let's see some associated terminologies that might come handy during this session. The first one is a node. As of for this document and during this session, a device that is supporting IFA functionality will be considered as a node. IFA zone is defined by a group of nodes starting where the IFA traffic is sampled and where it is terminated. So whatever we have from where the IFA traffic starts and where it's terminated, the switches that comes between that part is considered as IFA zone. And you might be seeing me using that term during my session. Metadata is telemetry as for telemetry specific and IFA specific is the data collected for each hop. Collector is a module attached to the terminator node, and it receives the IFA data and present it to the user either as a report or raw data. So let's move ahead with the details. So before diving or getting deep into IFA, just let's have a quick glance at what we mean when we say network telemetry. Let's look at some technologies and tools that supports it. First in line, we have SNMP, which, as most of you know, is where SNMP agents in the devices are queried to fetch data, for example, CPU usage, interface statistics, etc. This really helps in device monitoring because it tracks operational metrics such as uptime, interface status, CPU utilization, or memory utilization. Next in line, we have syslogs, which are kind of event logs generated for any events triggered by the switch. This includes error logs or configuration changes as well. The major thing about syslog is that it ranks logs based on their priority, such as warnings, alarms, errors, etc. So the next one is in the list is probably the most famous one, which is IPFix. It provides the details about network end-to-end flows, which include source and destination IPs, protocols, and bytes of traffic transferred. Uh, this provides visibility, which helps us to understand who is communicated to whom in the network and how much traffic is being generated. Next one, we have IPSLE. It is basically where a user generates synthetic probe packets to measure the network performance. Since a planned on-demand synthetic traffic is added in case of IPSLE, it should be noted that it brings an extra overhead traffic on the network. Moving ahead, we have SFlow, which gathers sample data at flow, packet, and interface levels. This includes details such as source, destination, IPs, ports, VLANs, as well as protocols. It's highly scalable due to its sampling and minimal overhead, making it suitable for large networks. So the next in the list is not a telemetry feature, but rather a web-based architectural style, which is used for network management and programmability via APIs. Its benefit is that it enables seamless integration with network controllers and third-party tools to move the network telemetry out of the box. Plus, the added advantage is that it is platform independent, is scalable, and easy to use. Now, coming to the final one is something what we are introducing for the first time in AOS-CX switches, which is IFA, which stands for in-band flow analyzer, which is an in-band packet telemetry method providing performance metrics such as latency, jitter, and congestion, which are actually enabled in the packets as they travel through the network. Now, IFA not just provides flow details, but rather provides hop by hop visibility in the network and helps the real-time detection of performance issues such as congestion or latency spikes. So talking about the brief definition, IFA is a real-time in-band hop-by-hop telemetry method that embeds your diagnostic information directly within the packets as they traverse through the network. Currently, IFA implementation is based on the solution details mentioned in IETF draft named as this, and as no such specific RFC is defined as of now. The purpose of IFA is to provide a near real-time visibility into your network performance, offering detailed insight into packet behavior at each hop. The key highlights includes it's a in-packet telemetry, which means that it is embedding telemetry data such as latency, queue depth, congestion into packets themselves, offering precise per packet insights. The major point is hop by hop visibility. It tracks performance metrics across each and every hop in the network, enable detailed analysis of how each device impacts your flow or your packets. So next is real-time monitoring. So the telemetry collected is in real time, is a near real time actually. That is 1 out of every 4,000 packets can be sampled at max rate, making it possible to detect issues such as packet loss, high latency, or congestion instantly. Benefits of IFA includes real-time troubleshooting because it quickly identifies performance bottlenecks. It reduces mean time of resolution. Plus, it provides granular visibility, providing deeper, more granular insights than traditional telemetry methods we have seen earlier in these slides, such as syslog or SNMP. It also enables proactive performance management by allowing network operators to detect and resolve issues before they impact the end users. Plus, it also helps to ensure that SLAs are met by offering continuous real-time insights across your entire network path. Talking about the product support, currently for this release, we are going to support IFA for our 9300 switches. That means both 9332D and 9300S models, with the future intent to bring this functionality on other switch families as well. It should be considered that IFA is a part of CX Advanced Feature Pack, which means CX Advanced Feature Pack is must to use this functionality. CX Advanced Feature Pack offerings for both 9300 models after 10.15 will be as mentioned. Both the models are going to support in-band flow analyzer, as you can see here. It should be noted that for IFA to work, switch must have an active CX Advanced Feature Pack installed, for which the orderable feature pack SKUs and the specific part numbers are mentioned here. It should be noted that IFA functionality will also be available if switch goes into honor mode or is put into honor mode. Now, if you want to learn more or understand more about how feature pack works, how it needs to be managed or installed on your switches, please feel free to refer AOS-CX 10.13 release update on CX feature packs. Let us now look at some use cases of IFA. Let us first understand the associated problem statement. So in a network with multiple hops, multiple nodes and hops, it might be complicated to analyze and diagnose network issues. Traditional monitorings or traditional telemetry features such as SNMP, NetFlow, or IPFix struggle to provide real-time visibility and moreover, the granular insights into the network performance, especially when the network is having multi-hop paths. These methods typically rely on out of the band data collection, which introduces delays and often aggregates data, making it difficult to detect microburst congestions and also SLA violations in real time. Considering the above issues, network operators face challenges in pinpointing performance bottlenecks, such as latency, jitter, and packet loss on specific hops, or detecting the resolving congestion and microburst before impact. This also hampers the user experience. Plus, they have no action to have a proactive approach towards these issues. Now, maintaining SLAs for latency sensitive applications such as voice, financial transaction, or AI/ML networks, this is very important, and this is where the issues are created the most. Also, network operators face challenges in troubleshooting network issues quickly in hybrid cloud and multi-cloud environments where the traffic paths are highly dynamic and visibility is very limited. So let's drill down at another level and look at a sample or a real life scenario which might help us to understand this better. So the scenario includes a large data center network, which is comprised of hundreds and thousands of servers and are interconnected via a significant number of network switches and links. The problem is that in such large networks, network performance anomalies such as packet loss, bandwidth decline, and bandwidth or latency jitters are major issues. This impact application performance and network management. Let's take a sample issue and consider a situation of packet drop. A switch in the network is facing packet drop due to congestion in data plane. Now packets are not forwarded due to this condition and application latencies are continuously rising. So the target for the network admin is to find the device facing issue and troubleshooting it. For example, it can be to redirect or reroute the network traffic. The challenges here is to minimize the mean time to resolve this issue. Plus, out of multiple flow paths, the network admin has to directly identify the path facing the issue with least network overhead. For resolution, I am going to talk about how multiple features fit in here and whether or not they are best suited solution for this issue. Let's first start with SNMP. So SNMP is unable to provide specifics of the issue. User can only see high resource utilization, and that is also only when the information is fetched from the device. Coming to syslog, it does not provide any congestion or packet specific event logs, as they are not specifically generated by the system. Only specific control plane event logs are delivered by the system currently. Coming to IPFix, it allows flow level details such as who is talking to whom, but lacks in granular details such as hop by of packet or latency information. Moving ahead, S-flow lacks the per hop visibility required to locate the specific bottlenecks and requires exporting the sample data to an external collector for analysis, delaying fault identification. Moving ahead, we have IPSLA, which generates the synthetic probe packets, which may not represent the actual application flows, leading to inaccurate results, and it monitors a specific predefined path, which may or may not have real conditions affecting the dynamic flows. It should also be noted that it adds certain amount of network overhead as well. Coming to trace route, a message in the case of trace route, messages may travel through a different path other than what was taken by the data packet, and the impact might not be that clearer. So you may get a false positive or negative. As a conventional method, you might go for ping as well. So ping can indicate the higher latency in the network, but hop by hop visibility is not there. Plus, it does not provide forward latency for each device in the network. Finally, we have IFA, which sends a probe packet to travel through exact flow path and keep recording the metadata, including queue depth, latency, and congestion metrics, which are readily available at the end device. It allows easy to identify device under impact. Plus, it maps the flow path traversed by the congested packet and devices hopped in the way. This helps to reduce MTTR as well. So based on the comparison here, it can be considered that IFA fits in well as the solution for this issue. Now, since we have two very close competitors to compare, or the two modern technologies that compare to each other, here is a brief comparison between IPFix and IFA. So IPFix is a protocol that for exporting flow-based data from network devices, whereas IFA is an in-band telemetry technique that provides fine grain, which means high resolution, hop by hop part trace with per hop latency and queue congestion. IPFix provides aggregated flow level information such as source and destination, volume, and duration of traffic flows. IFA provides packet level hop by hop visibility into performance metrics such as latency, jitter, queue depth, and packet processing time. IFA introduces additional traffic overhead by exporting flow records in separate streams from the actual data traffic, whereas IFA introduces minimal overhead since telemetry is carried in the data packet itself with no separate export traffic. Now, IPFix does not directly track latency or jitter. It can infer delays based on flow duration and timestamps, but is not precise. But IFA directly measures latency and jitter at each hop, giving precise real-time visibility into delay variations and congestion points. So IPFix stores historical flow data for long-term analysis and troubleshooting, whereas IFA typically provides real-time data that does not store historical information unless it is captured by external systems. And now as a last point, IPFix evaluate end-to-end flow, that means low resolution, whereas IFA evaluates sample packets from the flow data, which ends up making it a high resolution feature. Now, from above comparison, there is a bottom line that there's a key takeaway we can say from this is IFA does not replace the requirement of IPFix, rather it serves a different use case. Now, user can opt for either or both based on their use case requirements. So next we have there is another use case of IFA or where the IFA fits in really good is in the case of SLAs. So IFA can be leveraged to support SLAs and how we are going to see in the in this slide. So SLAs, just to give you a little bit brief, SLAs are crucial for business, especially in industries such as telecommunication, financial services, and cloud computing. If you're wondering, SLA stands for Service Level Agreements. These agreements define specific performance standards that providers must meet. That includes latency, packet loss, congestion, and jitter. So in case a business unit fails to meet SLA commitments, this can result in financial penalties, reputational damage, or loss of customer trust. Now, there are certain other factors that are oftenly associated with SLAs. These are SLIs, which stands for Service Level Indicator, which is a measurable metric used to track or quantify the actual performance of service against service level objectives. Now, again, explaining the service level objective is the internal operational target set by the provider to ensure they meet or exceed the performance levels outlined in the SLA. And SLAs are again a formal contract that defines the service provider's commitment to the customers regarding specific performance metrics and the penalties for failing to meet them. So it's a kind of funneled approach at the top of which sits the SLA. Next is the SLO, and then finally SLIs are the actual values of the metrics that defines or that supports those SLOs. So IFA can be leveraged as a major tool in meeting network service level agreements. It should be noted that IFA is very much complementary to IPSLA in supporting this use case and provides more granular details. It should be noted that IPSLA probe packet might not traverse the same path as the packet is facing as the packet facing issue already does. Whereas in case of IFA, this functionality is available and the packet actually traverses the same path as the original packet took and faced the issue. So here is one such example on how SLAs associated with respective SLIs. For instance, I am taking first one SLI as the latency, to which the connected SLO is to maintain the 99% uptime to ensure minor issues don't impact the SLAs. And the SLA defining it is that the end-to-end latency should not exceed 50 milliseconds between critical services, which may be between headquarters and a data center. And if latency increased by 50 milliseconds for more than 1 hour in a month, the customer receives a 10% fee reduction. Similar to this, we have two other examples, which is packet loss and congestion, and the associated SLOs and SLAs. Now, these are impacting, or these can come into play into different vertical or businesses. So let's look into a little bit of them one by one. The first one in the case of finance, where a real-time performance monitoring for financial mission critical applications is required. So such as high frequency trading networks in stock exchanges and financial institutions, where even milliseconds matter, trades must be executed with minimal latency, and network delays or congestion can result in significant financial losses. Now, IFA can help to diagnose these issues with such low latency networks. Please do note that this is about low latency networks and not the ultra low latencies. The banking and the payment processing system is the second. So we usually every day in our lives do number of transactions, which is provided by a number of global financial institutions, which rely on various payment processing system that typically handles these transactions daily. These systems support real-time payment transfers between banks, customers, and merchant across the world. The platform of performance is very critical because any delay, jitter, or packet loss can result in failed transaction or even revenue loss. Next, we have entertainment industry or the entertainment specific use case where real-time communication is very important, such as in voice or video where seamless communication is required. So in large scale, real-time voice and video applications such as video conferencing, what we are doing right now, or the gaming industry as well, the jitter and latency spike can degrade the user experience, leading to poor call quality or dropped connections. Next is another booming industry that we have is of cloud-based gaming platforms, where the cloud gaming platforms depend on low latency connections to provide real-time gaming feedback between game server and the player. Any latency spikes can cause lag or delays in the gameplay. Finally, we have AI ML networks with low latency requirements. So data centers that supporting low latency applications such as AI ML workloads, blockchain networks, or algorithmic trading platforms require deterministic low latency performance across the entire infrastructure. These were some of the examples where SLAs fit in, and IFA can prove to be a strong solution to provide the details in real time, especially around the network issues such as latency, congestion, and packet drops. Okay, now it's time to dive deep into details now. So the in-band flow analyzer is a feature. We have already understood that it allows users to monitor a network for faults and performance bottlenecks. IFA samples a user-defined flow of interest, whichever the user wants to configure, and generates special probe packets to collect telemetry data from an end-to-end path and per hop data path information. So in industry standard IFA implementation, IFA allows inserting metadata into live packets. So for instance, you have a flow coming from one source to another, and there are multiple packets in which in the industry standard IFA is done by appending the data or updating those packets with IFA metadata. But the current implementation for AOS-CX does not support this. Only a probe packet are supported, so which is done by sampling the flow, choosing a random packet and cloning it and then updating it with IFA metadata and then sending it again through the same path as the flow is taking. So there are three types of nodes that can be defined in IFA zone. The first one is initiator. As the name suggests, this is where the initiation of the IFA flow starts. It samples flow traffic and creates an IFA probe packet for each sample by adding IFA header and metadata to it. This is then further transferred to the transit nodes, which identifies IFA probe packets, checks the probe packet validity, and appends the node metadata after the probe packets IFA metadata headers. Finally, when the packet is taken their transit nodes and comes to an end at the terminator, this is where the termination of IFA flow comes into play. The packet is moved to the CPU, where its data is used to generate IFA metrics information for user consumption. Now, IFA packets must follow the same path as the original packets, and that's the strong zone of IFA. Sample copy of packets must be discarded at the terminator, and the original live flow goes to their respective location or wherever it was destined to. The metadata collected from IFA packet is extracted by terminator and is exposed to the user either via CLI or REST. Now let us view the feature functionality brief. Let's consider I have a host 1 that is connected to a switch which I have configured as the initiator. Now I'm sending some flow over this initiator, which is then further transmitted to your transit node. Now from the initiator, the IFA packet initiation will start, and initiator will sample the ingress flow data and insert its metadata into the IFA packets and pass it to the transit. There can be one or more transit nodes in the way, and where the transit nodes will keep on updating their metadata into the existing IFA flow packets coming from the back, and it will be passed on to the next node. Now, once this flow reaches the terminator will then segregate this. It will take out the packets marked with IFA, collect its metadata and present it to the user. On the other hand, the packets that were in the original flow will go to their destination as planned. It should be noted that initiator or transit can be configured on the same node, and hence if there is a transit in between, there is a chance that you can configure it as initiator as well. So a flow represents a series of packets that share common characteristics as they travel through the network. 5-tuple flow group packets are defined by these below parameters, which is known, such as which are source and destination IP address, source and destination ports, plus the protocol type. So below is an example of how IFA probe packets are modified versions of the sampled packets. Consider a scenario where I'm again sending some flow or some data from the host towards my switch, which is configured for IFA. Now, as soon as this packet reaches the switch, one of these out of number of packets, one of the packets will be sampled and it will be cloned further with this information. So the IFA probe packet will take over the L2 header plus the L3 header from the sampled packet and change it to 253. This will also include the L4 header as well. So all the headers will be taken from the original packet. Now the blue parts that you're seeing on your screen is where the IFA will update its data to this packet. It should be very critically noted that the payload that was originally part of that flow packet will not be considered or will not be taken by IFA probe packet. So this is this is how we have currently implemented it, and this is good because this removes the dependency and constraints which may be raised due to the NTU. So let's look at each node one by one and their specific functionalities. So at initiator nodes, the initiator node is responsible to sample the flow and clone the data packets. It also creates an IFA probe packet for each sample by adding IFA header and the metadata to it, as we have seen in the previous slide. It changes the probe packet protocol number to 253, and it supports unicast IPv4 and IPv6 traffic, UDP and TCP protocols, tagged and untagged packets, and aggregation links and multi-chassis lags, Both original packet and IFA probe packet sampled use same leg port member to exit. Initiating IFA is supported only at the system level or route only ports. On an initiator node, when the probe packet egresses, when it leaves the when it leaves the node after ingesting all the IFA metadata, it will contain an additional 40 bytes, which will include 4 bytes of IFA header, 4 bytes of IFA metadata header, and 32 bytes of metadata stack. Now, once again, MTU is not an issue as original packet payload is not the part of IFA packets. Now, the transit node identifies this IFA probe packet, checks the probe packet validity that it's still under the defined parameters, and appends the node metadata after the probe packet's IFA metadata header. Once this is done, it forwards the probe packet further. Now on the transit node, since we are not adding any headers, only the metadata is added, and that adds up a 32 bytes of IFA max metadata stack, which is inserted at each and every hop wherever there is a transit, causing the probe packet size to increase after each and every hop. Now, once again, I'll reiterate, since IFA packet does not include original packet payload, hence MTU should not be an issue. The max metadata stack length can be configured at initiator node to ensure the size of IFA packet will not exceed to some specified values, and we will see how this comes into play, how it needs to be configured, and what are the limitations of it. Coming to the terminator node, which is in case of CX 9300S, inserts its terminating node metadata into the probe packet and then moves the packet to the CPU where its data is used to generate IFA metrics information. Now this is very important because the behavior as a terminator for both 9300S and 9332D is a bit different. In case of 9332D models, switch will copy the IFA probe packet to the CPU directly, where the data is used to generate IFA metrics and information. So it should be noted that in case of 32D models, and if it's configured as terminator, it will not insert its metadata into the probe packet. Whereas this is possible, and this is done in 9300S, behaving as a terminator. Once this is done, terminator will drop the probe packet. So once again, this should be noted that IFA packet will move through 32D models in all roles as expected. It will support IFA data as an initiator, transit, or terminator. But just in case of 32D as an end node, which means that a terminator, it will not add its metadata before generating the final metrics. So this is about the details of IFA probe packets. Let's dive and look into it, what each of these fields really contains. So we have three parts of this packet, which is IFA header, IFA metadata header, and IFA metadata stack. The IFA header will contain these 5 fields where we have version. So version of IFA header will be set to 2.0, and then global namespace, which is set to 0x F. A protocol type, which is copied from the IP header from the original packet, and we have flags, which is unused right now. And then further we have max length, which is the maximum allowed length of the metadata stack in multiple of 4 octets. Now this value is user configurable, and this is what we will be seeing how to configure it and how it will be updated here. Next we have IFA metadata header. Again, the first 2 fields is not used right now. Now the last 2 is hop limit, which is the maximum number of allowed hops in an IFA flow. This value is again set by the initiator node. The hop limit is decremented as you take each hop or as the packet is transferred from one IFA node to another node. Finally, the current length of the metadata stack in the multiples of 4 octets. So what we have seen in the header is the max length, and here it will keep on updating the current length. So if this equals or exceeds the maximum length, the transit node will stop inserting its metadata. Finally, we have metadata stack, which have following fields. Quickly going through each of them, we have local namespace, which is set to 1. Next is device ID. This is something that is configured by a user to identify the specific node in the network. Next, we have IPTTL, which is egress port speed mapped with the IFA metadata. We have congestion field, which essentially indicates whether the packet has experienced some level of congestion or not. Further, we have egress queue port ID, egress port QID, and then we have received packet timestamps in seconds and egress hardware port number. Next, in line, we have ingress hardware port number, the receive stamp in nanoseconds, per hop latency in nanoseconds, which is the residence time. This is what we will be seeing in the final metrics as well. And then further, we have opaque data, which is 1, 2, and 3, which is regarding which will be updating or telling you the information about your queue depths. It should be noted that queue depths are considered or is mentioned in the units of cells. And to convert the cell into bytes, you need to multiply it by 254 bytes. So one cell is essentially equal to 254 bytes. Now, considering the feature implementation and how it is really configured on the switch. As a user, by CLI or via REST, you will be putting a telemetry profile on the switch, and we'll be seeing in the coming slides what this really means on your switch, which will be pushed to OVSDB. And the next you will be doing is to define the IFA or IPv6 class, which is again pushed to OVDSB further, and then following configurations of creating the IFA flow monitor and assigning it to the flow is again pushed to the OVSDB. Now all the other daemons, including the IPFix daemon and other daemons included in the above process, takes up their configurations from OVDSDB itself. So the respective daemons that will interact with OVSDB to get the latest configuration changes or updates. So now, as I was mentioning, we will be talking about flow telemetry profile. So each node in the IFA zone needs to be configured with certain parameters that define the specifications of the IFA packets that are reaching to that node. Typically, these details are needed to be configured on the initiator node, and that's where most of the details or most of the telemetry profile details are updated. Currently, only one profile is allowed at the system level, and there is only at the system level configuration available. So briefly, there is only one profile allowed. A flow telemetry profile is set up by the user to specify values for underlying parameters. And these parameters includes IFA device ID, and this is what we have seen in the IFA packet itself, which is a numeric value given to a specific node to identify it in IFA flow data. And this is user configurable, and user can choose a value based on their deployment. Now, this is optional requirement. In case user doesn't define any value, we have a default, which is which will be automatically assigned by the system. And the default is actually auto. By this auto, we mean that in case the default device ID is assigned to the switch, the load 20 bits of switch MAC address will be set as the device ID. And that's what the auto configuration means for the device ID. Next, we have IFA hop limit. So this is a value which is used on IFA metadata header for created IFA probe packet running as initiator. So this is the limit that you set up and is appended to your IFA packet itself. So in case of AOS-CX, only up to 10 IFA hops are supported on a terminator node. So if you are configuring your IFA zone, you should consider that only 10 hops will be shown on a terminator nodes. Only 10 hops of data will be added to your IFA packet or IFA flow. So there is IFA max metadata stack length, which in case of AOS-CX only LNS1 is supported, and LNS1 adds an IFA metadata stack with a size of 8 octets per hop. Next, we have sampling rate, which is a user-defined sampling rate at which the flow packets will be sampled. This is a very important field that user needs to configure. The default for this value is 4. Now the sampling is done in the multiples of 1000 packets, which means if the 4 is configured on the switch right now, one of each 4000 packets will be sampled. The range for this value is between 4 to 4 lakhs 20 or 420,000. So the respective sampling rate will make up to one packet. In case 4 is configured, one packet out of 4000 packet, and if so 420,000, it will be around 0.42 million packets. Only one packet will be sampled. The choice, getting back, the choice, it should be noted, the choice of a packet is fairly random. There is no criteria or the user capability to configure the choice of sample packets. Now consider a scenario, as was mentioning in the previous slides, where IFA hop limit is configured on the initiator is less than what's required to reach the terminator. So here is a case where I have multiple hops in my network and I have configured my hop limit on my initiator as 4. Now with hop limit configured as 4, only metadata of up to 4 hops will be collected, that is up to transit 4. Now what will happen after transit 4 actually? After transit 4 node, IFA metadata will not be collected anymore and will not be updated in the IFA flow coming from the back. But when it reaches to terminator, the metrics of up to only 4 packets or up to only 4 hops will be generated and displayed on the terminator. So the metrics that are associated for up to these 4 hops will be generated and will be displayed on your terminator. Now here comes the class definition. So IFA copies packets to the CPU using a IFA initiator type class, and this is again initiator specific configuration that needs to be done. So these classes are defined on initiator node, as I was mentioning, and IFA allows IPv4 and IPv4 classes to be configured. So an IFA class defines a match or ignore criteria for your ingress 5-tuple flow headers. This will include your traffic type, which can be UDP or TCP, because only UDP and TCP is supported for IFA, your source and destination IP address, and your L4 source and destination port. Based on these criteria, you will be asked to define a class for your IPv6 or IPv4 traffic. Now below is an example, or here is an example on your screen of IFA class defined to match the criteria for an UDP flow. So I have mentioned that the sequence as one match UDP, the source IP address, and the L4 port of source is equal to 80. Further, the destination IP address and the destination port is equal to 80. Now, when an IFA initiator monitor is configured, the system programs the hardware using these class entries as configured at that time. Any updates that are made to class entries after assigning it to an initiator monitor will for the applied initiators will be ignored. So for instance, you have defined this class and it is again assigned to a flow monitor. So if you make any changes after this assigning this class, it won't be accepted and ignored until and unless the monitor is reconfigured after making these changes. So then we have flow metrics at terminator, which is the final hop by hop IFA metrics that can only be checked via terminator. And currently terminator only supports, as I was mentioning in the earlier slides, either by a CLI output or REST to view these IFA metrics. The IFA metrics data at the terminator will include the total IFA packets received, which is the number of IFA pro packets received on terminator, and that are uninterrupted for last 5 minutes. We will talk about why I'm mentioning this uninterrupted for last 5 minutes. Next is destination IP, which is the IP address of destination switch, the source IP address, the IP address of your source switch, the destination port, your L4 destination port, and your L4 source port. Further, it will also contain the IP protocol. So it can again either be UDP or TCP. It should be noted that VRF detection, though VRF field is there, but VRF detection is not supported in current release. So it's set to be undefined. So next value that it will contain is about the network path latency, which will be the aggregate of residence time on each hop. Now, what does it really mean? So it will contain a network path latency, which is the aggregate of your hop by hop residence time, which for instance, you have three hops. You have T1, T2, and T3 as the residence time of a packet on each hop. How much time the packet has spent on these respective hops. By adding, you will be getting this network path latency metrics. Next, we have ECN hop congestion hop, which will mark the first node under the impact of congestion. It should be noted that when the ECN is enabled for to get the congestion, only the first node where the congestion is found can be displayed on your final metrics. And if you do want to view this congestion on your final metrics, ECN is a prerequisite. So once again, enabling ECN is optional, but it is recommended to be enabled if admin or the user wants to see network congestion information on the terminator. Now the congestion marked IFA packets will depend on ECN being enabled on the system. That's where I was mentioning that ECN is a prerequisite and needs to be enabled if the user wants to see congestion details on the end node. And due to this, it's only possible to identify the first node where congestion is found. Next, we have max hop latency, which highlights the hop details with maximum latency based on latest IFA data. Now it further includes two sub details, which is device ID, which is the device ID of the node with highest latency. So whichever node in the net in your path is experiencing the highest latency, that will be mentioned. The device ID of that node will be mentioned here. Second one is the latency, what that latency values really is. It will be mentioned here in nanoseconds. Further, it will also contain the terminator timestamp, which is the timestamp at which the latest IFF packet is received at the terminator. Next is the number of hops that has been experienced by the IFA packet, and will give you the count of IFA nodes configured on your network as well. Just below it, you will be having the device ID and how it is mapped together. For instance, it will show the hop by hop manner view of your devices and in terms of the device IDs. Now, I know I have talked through a lot of details, but here is a sample output to make it more clearer to you. So now here, if you see, we have total IFA packet received, which is 916. The destination IP is this IPv6 address, and this is the source IP. We have our 5-tuple details, which is destination and source port and your IP protocol. Now VRF is not supported with this release, as I was mentioning. The network path latency is around this, and the ECN congestion hop is with this device ID. Plus, there is a max hop latency detail. That means the device which is facing the max latency. So the device with this ID is facing the max latency, and this is the this is the latency value. Finally, we have terminator node timestamp. That is where the IFA packet is received on the terminator. And next we have number of hops that were crossed or that were experienced to reach to the final terminator. And this is how it is mapped together. So we have first device ID, second device ID, and 3 device ID, which comes under IFA zone. And this is how it's mapped. So apart from flow details, IFA metrics also includes hop by hop details for each node in the tabular CLI output. Now, this details will include the device ID for each node, the ASIC port number at which the flow ingresses. Now, it should be noted that IFA initiator node ingresses port will always, just for initiator, will always report as incorrect hardware ASIC ID. This is expected to be uh, changed or needs to be updated in upcoming releases. And this is just initiator specific as of now. Further, we have ASIC port number at which the flow egresses. So the port number at which the flow leaves the ASIC. And then further, we have speed of egress ASIC port in Gbps. Next, we have QID, bytes of data transmitted by specific queue, and the packets in the queue waiting to be processed. This is where the depth of the queue is measured. So egress queue depth cell defines the packets in the queue that are still needing to be processed. And as I was mentioning, this is mentioned in cells, which means one cell is equal to 254 bytes. Next, we have residence time, which is the time spent by a packet on a specific node. And this is mentioned as nanosecond. Further, we have RX timestamp, which is the instant at which last IFA packet was received on that particular node. In the last, we have number of packets marked with the congestion information, and this is where the ECN data comes into play. So in case you have enabled ECN, this is where you will be able to see your output in the congestion details. Once again, data from only first congested node will be displayed here. So here is an output of all-in-all view of your flow metric for a single flow. There can be multiple flow that can have similar outputs. This is for one flow. So on the top, you have your flow specific details. Below, you have your node specific details. And the similar metrics will be displayed for each flow data. Now, this is where you have at the top your 5 tuple details that were collected from the original flow header. Next, you will be having the flow level congestion and latency details, plus the node with device ID. So if you notice here, the node with device ID 908765 is experiencing congestion. The latency on the same node is with this value and for this metric for these many nanoseconds. This is just a sample output of how it should be looking. Now, once again, coming to the node level view, we can infer that out of 3 nodes, first node is having higher queue depth, which means NPU or the ASIC is taking more time to forward data packets. To determine the queue depth in bytes, you can multiply this value with the block size, that's 254 bytes. Next, we have the latency, which is also high for the same node, and the congestion is same for all the nodes because only the first node with the congestion will be acknowledged. Now, because this is where I can clarify a little bit, because the congestion is experienced by first node, this values is carried on the further nodes and not changed. So this is where you can notice the first node is experiencing the congestion. Further, we have in the middle the timestamp at which IFA packet was received at that particular node. And this is about the last IFA packet. Now we are moving towards a very, very important part of this session, which is the impact of IFA on TCAM. Now, as I was mentioning earlier, hardware support for IFA is enabled through the custom configuration of policy TCAM ASIC module, which means when configuring the switch for IFA, it is important to consider classifier policy and access control list configurations, as they may interfere with the desired outcome. As the TCAM module is used by multiple features for different purposes, usually for routing details, for traffic, other traffic-based features, hence it is considered as a limited shared resource. Now, due to this, these kind of features use TCAM to match traffic on some combination of header fields and taking an appropriate action against it. And these kind of features includes ACLs or policies. Due to this, creating an IFA monitors new initiation classes and or any other TCAM user rules are dependent upon the availability of ingress TCAM resources. Hence, if the ingress TCAM is near capacity or full, the ability to configure IFA monitors as desired will be very limited. Conversely, if there are large quantities of IFA entries already configured, it will limit the ability for you to configure other features that utilize those TCAM resources. So it is advised that switch operator must find correct balance of usage for the TCAM for all intended purposes. You can use the show resources command to monitor the allocated IFA ingress TCAM entries. Further, we have IFA support on VSX. So IFA over VSX lag is supported, including with transit packet routed through active gateway or through active forwarding. VSX sync configuration is also supported, and all IFA roles are supported on VSX, which includes initiator, transit, and terminator. If both VSX members are configured as, terminator, IFA traffic it will be terminated on the first VSX node where it is received. So because of this reason, it is recommended to retrieve the metrics on both VSX members. And this is important for the admin or the user. So if IFA flow needs to be initiated on the VSX, both VSX members must be configured as initiator. Otherwise, some packages might not be captured and flagged as IFA. Since each VSX member samples flow packets independently, initialization of IFA flows depend on which VSX member receives the flow. Sampling counts will start based on local IFA class entry settings, whatever you have configured on your class details, and the actual traffic that is being traversing to the VSX members. So both VSX members should be configured as a transit in order to include the device IFA metrics. This is required for traffic that could pass through ISL, and considering the fact that IFA is supported for traffic crossing the interswitch link. Otherwise, at the termination point, if IFA metrics information on the VSX member through which the sample packets traversed will be missed. These are some of the very important considerations when a user or a network admin is planning to configure IFA on their devices or on their networks. First thing, these are some of the details that I have picked out from the past slides, and this is where it comes handy to the reader as well. So the first thing is TCP and UDP traffic is supported. IPv4 and IPv6 and traffic is also supported only. So the congestion marked IFA packets, as I was mentioning earlier as well, depend on the ECN being enabled on the system. Because of the congestion depend of ECN, it was only possible to identify the first node where congestion is found. So ECN needs to be enabled on all nodes in order to get congestion metrics on the terminator. Now, this is not necessary, but it's the best recommendation because that's where you will be having your congestion details of wherever in the IFA zone you have a congestion or wherever the switch is experiencing the congestion. But even if you have ECN configured a one switch and not the other, and if that particular switch faces the congestion, that will be updated to your terminator. So the initiator nodes can be applied at interface or the system level, whereas transit and terminator nodes are set globally, which is only at system level. This means that any IFA packet marked traffic arriving at these nodes will be received by the system and will be given as a transit or terminate treatment, irrespective of which port it's coming on. It will be considered all as same. So the transit and terminator nodes are mutually exclusive. This is very important because you can configure initiator and transit on the same switch, but you cannot configure transit and terminator on the same switch because these nodes are mutually exclusive. You can either have transit on your node itself or the terminator can be configured. Now, initiator and either of transit or terminator nodes simultaneously in the same system is possible. So you can have initiator plus transit, or you can have initiator plus terminator configured on the same node. Nodes should not match. It should be considered that nodes should not match on the same flows as behavior is defined for this case, undefined for this case. Only one IPv4 and one IPv6 flow monitor can be configured, can be applied and allowed at the port level. Otherwise, the configuration will be invalidated. So you can configure only one IPv6 flow monitor and only one IPv4 flow monitor at system level. And system wide, an IFA and IPv4 and an IPv6 initiator can be programmed. Oh, so yeah. So this goes for the interface level as well. So for instance, you have an interface. You can only define one IPv4 initiator monitor and one. It's not or, it's one, it's and. So you can define one IPv4 flow monitor and one IPv6 flow monitor at port level plus at the system level. There is no prerequisite about ASIC to be configured as leaf or spine profile in the case of switch, in the case of leaf spine configuration. Now, IFA uses a hardware mirror session that does not interfere with mirroring or S-flow. Once again, hardware resources, TCAM and mirror session are required for IFA functionality. If resources are exhausted, IFA will not work properly and failure status will be reflected in show command on CLI or via REST. To obtain end-to-end metrics, all devices traversed by the flow need to have the IFA feature enabled. Otherwise, results can be skewed or undefined. The collector data, once again, is exported through REST API. And you can view it with a CLI as well. Now, in case user configures hop limit on initiator less than what is configured to reach the terminator, and this is what we discussed in the earlier slide, the IFA metadata will only be collected for specified hops, which you have initially configured on your initiator. The metrics can still be checked on the terminator. So once again, giving you an example, in a network, hop limit on the initiator is configured as 4, whereas the terminator is configured at 6th hop. So IFA data will be collected for first 4 hops and metrics is displayed on the terminator for just these first 4 hops collected data. For rest 2 hops, the data will not be collected. Now on terminator, the IFA packet cache uses a basic aging mechanism, and that is where we say that flow should keep on updating or flow packet should be keep on coming so that the flow cache should be updated in the metrics regularly in this period of 5 minutes. So IFA packet cache uses the basic aging mechanism that deletes the flow if they are not updated within 5 to 6 minutes. So if there is a flow that has been displayed on your IFA metrics data, and if no further packet is coming for the same flow for last 5 to 6 minutes, it will delete that data from the cache. This means that if an IFA packet for a flow is not received during this particular time, the flow is removed from the IFA packet cache. Now, as a terminator, 9332D does not include its metadata into IFA metrics, whereas, as we have seen, CX9300S does. Please do consider that there is no MIB for IFA details as of now, and hence there is no SNMP support. Interoperability with other vendor switches, it's not currently supported. Broadcast, unicast, unknown unicast, or multicast traffic are not supported. Now, Initiator supports IPv4 and IPv6 unicast traffic with following exceptions. The IPv6 with extension header is not supported. TCP packets with options are not supported, and the 1588 UDP frames are also not supported. IFA in VXLAN fabric is not currently supported, and the IFA initiator node ingress port will always report an incorrect hardware ASIC as of now. Now, user cannot configure different sampling rates for different flows on the IFA initiator interface. So if you have seen, we have single profile and we have only single entry for IFA sampling rate, and that's where the system will and that rate the system will sample all the flows. Quickly moving through the configuration part, since we have a feature pack as prerequisite, we have to verify the current feature pack and the advanced feature pack feature state, and which can be done using the following command. So for me, as you can see, this is a 9300 switch. We have following advanced features, and the feature pack is currently active. Now again, this is a kind of prerequisite. If the user wants to see the congestion data, ECN should be enabled. So user can create a threshold profile defining one or more queue threshold configurations with a particular ECN action, even if it doesn't matter even if the DCB or Rocky V2 is not used on the switch. So then you can apply the threshold profile globally on all ports, or apply the threshold profile as a specific port override to any ports that require ECN behavior. So for this purpose, you can use this particular command to assign this particular ECN profile. This is at the system level, and then once again at the interface level, you can go into the interface context to assign this particular profile. Now, please do note, even if the IPFix daemon is actively involved in IFA feature functionality, there is no prerequisite to configure IPFix on the system, and there is no as such impact on already existing configuration on the switch. Even if ECN is not configured by the user, they can still infer the congestion by looking at the queue depth and latency data, and hence ECN configuration is purely optional and depends on the user or the network admin.
Okay, so now it should be noted that ECN as a feature can be configured in different scenarios, or as a user, you might have configured your ECN on different switches, and there can be multiple scenarios as such for these kind of deployments. So let's see few of them and how it will impact the usage of ECN feature and in context to IFA congestion. So in case one, I have a network deployment where host 1 is trying to contact host 2, and I have an initiator, a terminator, and I have 6 transits in between. So for this deployment, you can see that I have not enabled ECN on my first 3 nodes. Rather, I have enabled the ECN feature for all my later nodes, including the terminator. So in this case, how or what will you be able to see the congestion on your terminator or not? So first thing, in this case, if the congestion is experienced on transit 3 or prior to it, terminator will only show transit 3 as the first node to signal ECN congestion. Now, if for some reason initiator or transit 1 or transit 2 are congested, terminator won't show this information because ECN is off for that particular switches. As another scenario, I have case 2 where I have the same type of deployment, but I have enabled my ECN feature only for one of the nodes in between. That's for transit 4 in my case. Now in this case, user will see congestion marked packet starting on the transit 4, and for any nodes afterwards, the IFA packet will already marked as found congestion, and it will be traversed through the further nodes and reach to the terminator. And the terminator will show congestion on node 4, and that's how different scenarios will work in terms of ECN features. Again, I'll reiterate this thing that whenever you have congestion on your network, only the first node that is facing the congestion can be acknowledged by IFA and shown on terminator.
Coming to the IFA specific commands, we have the step 1 is to set up your flow telemetry profile on initiator, which is the first you need to get into your flow telemetry profile context and then update the following parameters, that is device ID, hop limit, max metadata length, and the sampling rate. Next, so further you have to configure a device ID, and the device ID will be visible. This is the same ID which will be visible in IFA report or metadata on the terminator. Now, auto mode is the default for this configuration. In case auto is left on the system, lower 20 bits of switch MAC address will be considered as device ID. So the negative values are not allowed to be configured. Plus, you cannot use any string, any character values. You can only use the numeric values. No version of this command resets the device ID value back to default, which means low 20 bits of MAC address. Further, we have IFA hop limit. The currently terminator can show up to 10 hops of IFA metadata. So if more than 10 hops are configured, metadata of first 10 hops will be considered and shown in your final metrics. The default value is again 10 for this IFA hop limit in case no user value is assigned. So 0 and negative values are not allowed to be configured as hop limit. And no version of this command is again resets the hop limit value to default, which is 10. Further, we have IFA max metadata stack length, which is a user-defined value used for IFA packet header. This is 80 by default. Now, AOS-CX adds an IFA metadata stack with a size of 8 octets per hop, which means stack length is verified on each hop to make sure if does not violate configured max value. Again, similar to max hop length, this is having a default as 80, and you can configure it between 8 or 248, which is its allowed range. The negative values or the values smaller than 8 are not allowed to be configured. Values are not necessarily required to be multiples of 8. Any values defined in the interval is acceptable. For example, 164 or 217. Behind the system, it will just accept in the nearby 8, the value that is divisible by 8, and that's what the system will accept. So the no version of this command resets the max stack length to default, that is 80. Next, we can configure the IFA sampling rate. The AOS-CX can sample incoming flow data as per defined value, whatever user wants to define. The default for this value is 4, which means 1 out of 4,000 packets will be sampled. IFA sampling rate is configured in the multiples of 1,000 packets, and this is the reason why 4,000 packets for 4. So this means if 4 is configured, 1 out of 4,000 packets will be sampled. In case the upper limit, that's 420,000 is configured, it will be around 0.42 million. Now the value should be only between this interval, and the no version of this command resets the sampling rate to default, that is 4. Next, we have to configure the class, IFA class, and this is how we need to define the class. So the class definition is subjected to the type of flow or type of IP flow. For instance, the class needs to be IPv4 type of class or IPv6. So you need to choose one of them. We have the option for IP and IPv4 and IPv6 class separately. Once you have chosen your flow of interest and the type of flow of your interest, you can insert the class name, and then further it will take you to the class context where you will define the match or ignore criteria. This is where it will take your 5 tuple details with the sequence number followed by your match and ignore criteria. So for instance, I have now added one match. Now I have option to choose the protocol of my interest. Once again, we have TCP or UDP supported by IFA. In case you configure any as well, only TCP and UDP traffic will be accepted. So the current version of IFA supports TCP and UDP protocols. And once again, if you configure any, it will also work, but just it will accept TCP or UDP for IFA metrics. Once you have chosen your protocol, it will be asked, or you can enter your source IP address. In case you don't want to do that, you can leave it to any as well, in which case any IP address from that of that specific traffic type, which means UDP, will be accepted, and the any is basically available for all the further categories. So for instance, I have I have the option to configure the source L4 port, but if I don't want to configure it, it will automatically go for any L4 port. Further, you can enter the destination IP and destination L4 port address, port number. Now, the final match criteria for a defined class can look something like this. One match, UDP is your protocol, and you have specific IP, your source L4 port, destination IP and destination L4 port. You can repeat the above process to create more match or ignore criteria for each class. It should be noted that you can define at max 50 match or ignore criteria or class entries. So similar steps can be followed to define ignore criteria as well, what we have seen for the match above. No version of above command will be used to remove a criteria. Further, we have step 3, which is to configure the flow initiator monitor and assign a class. Now, to assign, this is where you will define IFA flow initiator monitor. To access IFA initiator monitor context, you will use this command. Once you'll use this command, but before that you have to define the initiator name as well. Once you give initiator a specific name, it will take you directly to the initiator context. And this is where the flow filter class will be required to associate with your specific monitor. And this is where it should be considered that class should be already defined before you assign it to a specific flow monitor. And it's a kind of prerequisite. So the only one class can be assigned for each definition of IF initiator monitor, which means if you have multiple classes, you can only define or insert only one flow filter class. You can have multiple criteria on that specific class, but you can only assign one class per initiator monitor. Now, if class is not defined, as I was mentioning, or class with specified name does not exist, CLI will show the below message, which means then when invalid flow filter class is assigned. Once you have defined your initiator, you can assign your initiator to the system or at port level. Now, applying IFA initiator monitor to the system level, you can use below command to assign it to IPv4 flows. Below command can be used, which includes IP flow initiator monitor, and then further you can name your initiator that you have created before while defining the initiators. In case of IPv6, you will have to go via IPv6 flow and then update your IFA initiator monitor. It should be very carefully noted that the class entry or the class type should be same as the flow definition. So for instance, if you are assigning this flow monitor to IPv6 type of flow, your class type should also be IFA IPv6 type. So further, we have the option to applying IFA initiator at the interface level as well. The same process can be followed, but this needs to be done in the interface context. So for whichever interface or interfaces you want to give this assign this particular initiator monitor, you can go into that particular context and follow the same flow for IPv4 and IPv6. So this is where you can insert your flow monitor, assign your flow monitors to multiple interfaces. Further, you can remove your IFA flow monitor initiator monitor using the no command of the no version of the same command. Now, when an IFA initiator monitor is already configured, the system will program the hardware using the class entries as configured at that moment when you created that particular initiator monitor. So any updates when you make in that class entries after assigning it to a particular initiator, for instance, you're changing the destination port, or you're removing a criteria, you're adding a criteria, will be ignored until and unless the monitor is reconfigured, which means you have to unassign the class and then once again you have to assign it to the monitor itself. Now to make these kind of changes, it is required to update the class entries. First, you have to update your class entries, whatever change you want to do in your class, in your existing class. Then remove the IFA initiator monitor using no command. And then once again, reapply it. So you don't have to reassign the class, but rather you just have to remove your IFA flow initiator monitor and then reassign it to your particular system or interface. So further, for the transit and terminator nodes, there is no requirement to configure flow telemetry profile on this particular nodes. But if the user wants, they can define the device ID based on their deployment type. And this is fairly optional. If this is left to default, again, 20 bits, lower 20 bits of MAC address will be included. So there's no requirement to configure transit or terminator at port level because it is only allowed to be configured at system level. IFA flow monitor is configured for transit and terminated at system level and can be achieved by this command. So you will use IP all, which marks all types of IP flows, and then you can choose either of terminator monitor or put it as a transit monitor. So if you want to make it as a transit node, you will go with transit, and in case you want to go with terminator node, this is what you will be doing. Again, no version of the above commands will remove the active flow monitors. Once again, because these details can be configured on the switch via REST, this is where I just will talk a little bit about how to configure these details on the switch via REST or the switch UI. So to get the update or details of the current telemetry profile, you have to look at flow telemetry profile details. Further, you can first get the current flow telemetry profile that has been configured on your switch. So you can use the get operation to display the current telemetry profile that has been configured. And this is what it will show you, whatever the details will be mentioned. Please make sure that you enter a depth to traverse as 2 so that it can list down values configured for current parameters of the profile. Now again, this is all about how to view those details, but if you do want to update the flow telemetry profile on the switch, this is what you will be using. You will be using post method, and wherein you will be inserting your respective values of these parameters. Now, if you want to configure flow IFA initiator monitor on the switch, first of all, if you want to get the details of currently configured IFA initiator monitor, you can use IFA initiator monitor flow monitor and go use the get method. Once you use the get method, once again, add the traverse depth as 2 to list down the details of each parameters. If you do want to configure the flow IF initiator monitor on the switch, you can use the post method and assign this specific class, because the class is what matters to initiator flow monitor, to this particular parameters, and then you can click to apply. Further, if you want to assign this particular generated flow monitor to the system level, you have to go to the system tab. And if you do want to understand if there is any initiator assigned to the system, you can go through the get go use it by the get method. And if you see in the output, it will be updated as IFA initiator flow monitor and which initiators is configured right now. It will list all the initiators actually. So for me, only one initiator is configured, since this is only one is listed here, plus the type of initiator. Now, if you do want to assign an initiator to flow monitor to the system, you can use the patch method where you can assign initiator flow monitor name to this particular field and then update the switch. If you want to do the same for the interface level as well, you can repeat above steps at the interface step. For configuring IFA node as a transit or terminator, all you have to do is to use the patch command, a patch method, and under IFA flow monitor field, you can enter transit or terminator keyword, which will make it available, which will make the node to behave as either of them. Now, if you want to check IFA metrics on your terminator using REST, you can perform the get operation on invent flow analyzer metrics, and setting the traverse depth to will show you all the details of your specific parameters that are shown and that are included in the metrics. Coming to the best practices, you one need to ensure that the IFA max metadata stack length aligns with the IFA hop limit value. For ease of management, it is advised to have device ID, which is easily identified for each node. If for example, one option can be to leave it as default, that is auto, which means the lower 20 bits of MAC address will be configured for the device ID. Now, to get the congestion details for terminator, you need to ensure that ECN has been configured on all nodes. Switch operator must find the correct balance of usage of the TCAM for all intended purposes, because this is a shared resource and IFA configuration does impact the TCAM when considering when the admin is really considering to configure IFA on their deployment. Moving to the troubleshooting part, you can use the to view the IFA class, you can use the show command, which is show class, which will show you the all the classes configured on your system. If you want to be more specific and want to see IFA specific class, you can define IFA IP or IFA IPv6 class. This is how your classes will be displayed on your system. Now, if you do want to see your flow telemetry profile configured on the switch, this can be done by your show running config. This is updated in the same. So if you want to see, you can use the flow running config where these details are updated under flow telemetry profile. But if you want to be specific and just see flow telemetry specific, flow telemetry profile specific output, you can be more specific and type show running config flow telemetry profile, which will list down all your specific configured parameters. Now, in case default flow telemetry profile or the default parameters are configured, that will not be shown in the above output. So the flow initiator monitor details, if you do want to see that, you can use again show running config. And if you want to be more specific, you can use show running flow IFA, which will show your flow telemetry profile as well as your flow initiator monitor. Uh, be it any number of initiator configured on the switch, it will be mentioned here or it will be listed here further with whichever flow filter class entry has been assigned to it. So the default flow telemetry profile configuration is once again will not be shown in the above output. Now, if you do want to check the TCAM entries, this is what you can use. You can use show resources command. For me, I have configured one IFA initiator monitor assigned in system level. And this is the really important part, because when you assign your initiator to your when you assign initiator to your system, 9 entries will be added. That's 6 for general IFA initiator and 3 for sample flow. This is just for the first one. So as you move and add more initiators to your first node or your initiator node, it will keep on adding 3 sample flow, which will increase the entry count by 3. So it's 9 for the first, then 12, then 15, and then 18. In case of transit, TCAM entries again can be verified with the same, but in this case, the entries are constant because it's assigned at the system level and only one entry is there. That will be of 2.
So in case of Terminator, there lies a bit of difference in how both our switch families are going to behave. And we have discussed this earlier as well, that in case of 9300S, you will find that it will include its metadata when behaving as a terminator, whereas 9300 32D models doesn't. So here we'll see at the TCAM level how both of these models are different as well. So in case of 9300S behaving as a terminator, you will see that three ingress TCAM entries will be reserved when you assign a terminator monitor for 9300 S switch, as well as you will see that two egress TCAM entries will also be included in the case of 9300S. Now, it's to be noted that egress IFA entries will not be configured in case of 9332D switch and will only be configured in case of 9300S family. To highlight this point, to make a little bit more clear, here is a view, or here's a difference. So this is the output of 9332D when defined or when configured as a terminator. You will see that only uh, ingress TCAM has been taken or has been configured for with the entries. And here you can see the ingress TCAM is only configured. So I have assigned it the terminator monitor, which essentially goes as a global level. So you will see three ingress TCAM entries are defined for this particular node or particular switch to behave as a terminator. Now here is a consolidative view of what you can expect when you are configuring different switch families as particular nodes and what kind of TCAM resources will be used. So here is a consolidated view of what we have discussed in past three slides.
So IFA status monitor, this is where you can see all your monitors that you have configured on a switch, be it transit monitor, terminator monitor, or your any initiator monitor. So if you are seeing it on the initiator node with the IPv4 or IPv6 configured and no port specific initiators configured, that is what you will be seeing. You will see two initiators of type IPv4 and IPv6 with active and active status. And if you have configured it for some specific port, that will also be included in this output with target state. Probably if it's active, it will show as active. If it's under progress to get active or there is some issue, there is still some process needs to be done, that's in programming. And if there is an issue, it will, or if you are removing it, the initiator from the switch, it will be shown as unprogramming. Now, once again, these are some of the status that can be shown on your initiator node with a particular error or on port configuration. So where you are seeing the pre-error states, these values can be updated and the same. So for instance, you have a particular error state that will be updated instant of a target state and will be shown here. On terminator and transit nodes, your IFA flow monitor will show one entry and that will be terminator IP all target state active if it's working fine, or the transmit IP all target state active. Finally, we come to the final output, which is to view final outputs as a terminator, which means terminator can display, since terminator can display full information about current IFA flows. Timestamps will be displayed in UTC. If brief is specified, then the flow IFA metrics summary will be displayed. Now, what do we really mean by summary? So, show flow IFA metrics has a brief subcommand. And when you use that brief subcommand, you will be able to see what IP destination and source the flows are moving to, the destination and source ports, plus the IP protocol. Probably only your 5-tuple details of all the flows that are coming to your switch via IFA. But now when you dive into the IFA flow metrics, you will be able to see all these details which we have discussed in the past slide for each and every flow. This is only for one flow, which is coming from from source IP 5 to 8, but this will be repeated for all other flows, which means from 7 to 4 or from 1.1.8 to 1.5. The following events log will be generated in context to IFA. So there is a long list, and this will include your feature pack specific issues or your monitor specific issues, or in case your IFA initiator faces or IFA monitor faces any type of error in the middle. Now the green part is the variable because there might be different situations in which these errors are generated. If you do want to check what these highlighted parts can be of, there are different types that can be updated in these specific fields, and a new error will be displayed or new event will be generated with these specific details. So now again, for enabling the debug for IFA, you can use debug flow telemetry IFA command. So now it's time for a quick demo to show the brief functionality of this feature and how it's coming into play. So this is what my demo setup looks like. I have 3 devices sending data to my initiator with these respective IPs, and then it further is passing through one transit node and moving towards the terminator. So device 1 is sending the flow to device 4, both TCP and UDP type, and the same goes for 2 and 5 and 3 and 6. My current configs include device IDs at respectively 1, 2, and 3, a hop limit as 3, a maximum max data stack length as 24, sampling rate as 5, which means 1 out of 5,000 packet will be sampled for my demo setup. This is the class definition I have defined. I have defined one initiator class with IPv4 type. And the filter class entries include 1, match UDP from any source to any destination, and 2, match TCP to match any source to any destination. So let's look at this demo. So this is what I have generated as a recorded demo, and this is what my nodes look like from the CLI point of view. The first thing I'll be doing is to check the feature pack status on each node. So for initiator, the feature pack is active and running. For transit nodes, the same. And for the terminator node, it's the same as well. Now, the second thing I will be doing on this is to go back and show if any current telemetry profile has been configured on the switch. But before, I'll just show in case I have any flow level metrics being generated at terminator, which should give me nothing because I haven't configured any details on either of these nodes. So I'll go back to my initiator and I'll perform a show running config, and this will show me flow or flow telemetry profile. And if I do the flow telemetry profile, there is absolutely no output because I have no profile configured. So now I'll go ahead and configure the flow telemetry profile. So the first thing, these are the respective parameters that I need to configure. The first thing I'll be doing is to assign the device ID to the specific device. So definitely now I have assigned the device ID, plus I have inserted a hop limit as 3, and IFA max data stack length is being defined as 24, similar to what I have mentioned in my demo slide. IFA sampling rate is defined as 5 for my profile. And I'll exit this context. And now if I do the show running config flow telemetry profile, I will be able to see my information or telemetry parameters being configured. Now what I'll do next is to check if I have any classes assigned to it. And if I check for IFA, I have no class configured as of now. So I'll go ahead and configure a class for my IFA IPv4 type traffic. So it will be class IFA IP, and I'll assign a name to the class, probably class initiator v4 or class init v4. Yeah. Once this is done, I will be in the context of class IFA IP, and I have list or ignore, I have match or ignore criterias for me, and I will be having match criterias configured here. Remember the two entries. The first one is for TCP for UDP traffic, and the other one is for TCP traffic. So I will configure it for my TCP traffic, and this will be from any to any. I have particular options to assign a specific IP address, but I will leave it to any IP address source to any destination IP address. And since I haven't defined the specific L4 port numbers, it will be automatically taken as any, or it will accept any L4 or destination or source port. Similar way, I'll define the match criteria for UDP, and the same way it will be any and any. And I'll exit of this class context. Now, if I do show class, I will be able to see my class configured. So here are the class, the match criterias, and the protocols. All your 5-tuple details that you have configured. Now I'll go ahead and assign this defined class by creating a flow initiator monitor. So this is where the class comes as a prerequisite to be added to your flow initiator monitor. So you have flow and you have IFA initiator monitor. Now it will ask you for the name of the initiator you want to give. Now, once again, please do note I am configured. I am defining a name that is easily identified to the user, and it's giving you the name of choice because you can define multiple initiators on your switch. And it is just about the definition. You still have not assigned this particular initiator monitor to respective system or specific ports. So I will add the flow filter class entry in flow initiator monitor context with the specific name. And remember, the class name is important because that's what you will be using to define that particular class here. So I have init class v4, and it will be accepted here. Once again, going out of the flow initiator monitor context, I'll do a show running config, and I should be able to see all these details appended there. So if you see at the top, I have flow telemetry profile details. I have my class details in there, and I have my flow initiator monitor as initiator 1 with the specified class, that is init class v4. So now we are all set to assign this particular initiator to particular flow of my choice. So I am choosing to assign this initiator to system level and for any IPv4 traffic coming to it. So I'll use IP and flow. If I would have gone for IPv6, I would have chosen the IPv6 command instead. So I'll go with IP flow and then IFA initiator monitor, and then define the name of initiator monitor that I want to assign. So I'll add it as initiator 1, and it's done. So we have now successfully assigned a flow IF initiator monitor to system level. And this is where you can once again see this output in your running config. So the IP flow IFA initiator monitor is now configured for initiator 1. And if you do want to see your flow IFA details, you can use flow IFA and your monitor status. So if you see the monitor status all, you will be seeing all the monitors that has been configured. For me, it's at system level, just one monitor, and that too for IPv4 type class, and that's working and it's in active state. So I'm all done with my initiator now. Now let's jump towards the transit node. And this is going to be quick because we don't have to perform any kind of class definition or assigning or defining the profile itself. But just as a best practice, I will define the device ID for this transit and give it and mention it as 2. So I'll you once again get into my flow telemetry profile context and insert those values in there. I have flow telemetry profile and I will append the device ID because this is where it will help me to identify the device easily. So I have device IFA device ID mentioned as 2, and I will change nothing else on this side and I'll exit of this out of this context. Now to make this node as a transit node, I will, since it's at its system level, it will be taking over or it will be applied to all IP flows. Checking as of now, you will see show flow IFA monitor status all. You will see nothing configured because I haven't still made it the IFA transit node. So now I'll go ahead and type IP all. And further we have flow. And next in this command, we have two options, either of IFA terminator monitor or the transit monitor. So I'll go ahead and I will choose the transit for this node. So I'll type IFA transit monitor. And it's done. So my transit monitor is applied to my node now. It should be behaving as my transit node. Now, once again, if I do show flow IFA monitor status all, I should be seeing my transit node as active and see. So that system level, we have transit IP all. The target state is mentioned as active. So finally, we are done with both our initiator and transit, both are in active state. Now the final thing we need to do is to configure the terminator. Again, this is not going to be a very big part because on terminator also you have to just assign terminator at system level. No profile or class level specifications are required. So before I do any specific configurations, I just want to show that we still don't have any metrics shown on the terminator because we haven't still made it a terminator itself. So if I do show flow metrics, it's showing me absolutely nothing. Now, once again, I will go ahead and I will add a device ID for it, which is 3. Flow telemetry profile, device ID, IFA device ID should be 3 for this one, and I'll exit out of it. Similar to transit node, I will again use IP all to make this as a terminator node. So we have IP all, flow, IFA, terminator monitor. And it's done. So if I check out the status of this as well, I show IFA flow monitor status, it will show me as active terminator. Now, once again, let's type the metrics command and see if we are getting any output for our flow. So I'll type show flow IFA metrics, and first I'll check the brief. So if I see the brief, you can now see that I am getting my flows coming in on my terminator. This is the 5 tuple details for that. Once again, I'll use the show flow metrics And here is the final output of the flow. This is what we can finally see. My flows are successfully coming to my terminator. Now, one thing that needs to be carefully noted down here is that because this is a 9300 switch, so we are not getting third hop detail or the terminator details in there. We only have 1 and 2, so the details of the terminator is not appended to the final matrix. I'll show the similar output with same setup, with same devices sending the data to same destinations using deployment of 9300 switches as well. But this is where your all the details are coming in, your 5-tuple details and your node specific details as well. So now I have changed my system. I am now having the same setup done for 39300S switches, and I have configured all those details on it. I just will go ahead and do show flow IFA metrics. And so flows are coming in the brief. I will just do the final IFA metrics. And as you will be able to see in this output, you are seeing all the data for all the 3 nodes in the network. So there is a brief difference between 9300 and 9300 switches that we were talking about in the slides as well. These are the node specific details. So let's move back to the slide deck. Now this is where we come to an end of this session.
To get regular and latest updates on our products and solutions, please join Airhead's community. Here is a QR code to make the process easy and hassle-free. Thanks a lot for watching this video. Stay tuned for the upcoming sessions.